All right, today we're going to crack the code on a classic computer science problem. And the solution? It's so elegant, so intuitive, you'll probably wonder why you didn't think of it yourself. Let's dive right into the fast and slow pointer technique.
So picture this. You've got this long chain of connected links, but it's so long you can't actually see the end. And the only thing you're allowed to do is move from one link to the very next one. How in the world would you figure out how to stop exactly in the middle? Well, that's the core challenge we're going to solve today.
To really get our heads around this, let's just forget about the code for a minute. Let's set it aside. Instead, we're going to reframe this whole problem as something way simpler, a race.
So welcome to the pointer race. This simple analogy, believe it or not, is the key to unlocking the entire algorithm.
This analogy actually maps perfectly to our data structure. Just think of the racetrack as our linked list, that sequence of connected data points. Each runner is what we call a pointer, which is really just a fancy word for a marker that keeps track of our position on that list. And the finish line? Well, that's simply the end of the line, the final point in the sequence.
Okay, so the analogy makes sense. But how does a race actually help us find the middle? That brings us to the core logic of why this thing works so well.
The whole technique is named for our two runners. We have a slow pointer and a fast pointer. And just like the names imply, they do not move at the same speed. One is exactly twice as fast as the other. And this simple difference in speed, well, that's everything.
The rules of this race are super simple. Rule 1. Both runners are slow and fast pointers. They start at the exact same place, the head of the list. Then, with each turn, the fast pointer jumps forward 2 spots, while our slow pointer just moves forward 1. That's it.
And this brings us to the real aha moment. This is the key insight. By the time the fast runner hits that finish line, where do you think the slow runner is going to be? Exactly halfway. It just makes sense, right? In the time it took the fast pointer to travel the full distance, the slow pointer, moving at half the speed, could only have traveled half that distance.
Now, that logic sounds really solid, but hey, let's prove it. Let's do a quick dry run with a simple linked list and see this race in action for ourselves.
All right, here's our track, a simple list with 5 nodes. You can see our slow pointer, S, and our fast pointer, F, are both lined up at the starting line, right there on node number 1. Okay, first move. And they're off. The slow pointer advances 1 step, landing on node 2. In that same turn, the fast pointer leaps 2 steps ahead all the way to node 3. So far, so good. And now for the second move. Again, the slow pointer just takes 1 little step, landing on node 3. Meanwhile, the fast pointer takes its 2 big steps and lands on the final node, number 5.
And boom, that's our stopping condition. The fast pointer has hit the finish line. It can't move any further. The race is officially over. So, the big reveal. Where did our slow pointer end up? Right on node 3, the exact middle of our 5-node list. The logic holds up perfectly. It just works.
Seeing it play out visually is great, but how does this simple logic actually translate into real code? Let's take a look at the blueprint.
So if you look at the code here, in both C++ and Python, you can see how directly our little race translates. It's almost 1-to-1. First, we set both our slow and fast pointers to the head of the list. That's our starting line. The while loop, well, that's our racetrack. The race keeps going as long as the fast pointer and the spot right after it aren't empty, which is just a safe way of saying the fast runner hasn't hit the finish line yet. And inside that loop, those are our rules of movement. Slow moves 1 step, fast moves 2. Once the loop is done, we just return slow because we know it's sitting right there at the midpoint. It's that simple.
Any good algorithm needs to be robust. So what happens when we throw it a curveball? What if we don't have a nice, simple list with an odd number of nodes? Let's put our logic through a little stress test.
And what's really great is that our algorithm already handles these weird cases without any changes at all. If you have an even number of nodes, the fast pointer just stops safely at the very end, and it leaves the slow pointer on the first of the 2 middle nodes, which is usually what you want. And with a single node, or even an empty list, the loop condition just isn't met, so it never even starts the race and returns the correct result right away. It's just incredibly efficient.
So what are the big takeaways here? Well, first, that a really simple analogy, like a race, can make a complex problem feel totally intuitive. Second, the entire technique just hinges on that simple 2-to-1 speed ratio. That's the secret sauce. Third, this is a universal pattern. You can pick this up and apply it in any programming language you want. And finally, the most elegant solutions are often the ones that handle all those tricky edge cases without needing any extra complicated code.
And that kind of leaves us with a final thought. This pattern of using 2 pointers moving at different speeds, it's incredibly powerful. Finding the middle is just one application, so it makes you wonder, where else could it be useful? What if, for example, our racetrack wasn't a straight line? What if it was actually a circle? Well, we'll leave you to think on that one.